Fluke 9010A Microsystem Troubleshooter was introduced around 1981. It was designed to troubleshoot and test microprocessor-based machines, hence the name. Today, the system is still widely used, especially in the arcade collector scene, to troubleshoot vintage arcade PCBs, but can of course be used to fix any kind of vintage computer system as long as the target machine's CPU is supported. In its base configuration, it consists of a control unit called the mainframe and a pod to interface with the unit under test, the UUT. The I/O section of the pod offers over and under voltage protection for all signal lines, allowing the pod to be used in electrically hostile environments, to quote the manual. Additionally, a probe can be used to detect logic levels and calculate node signatures, as well as inject pulses into the circuitry. The 9010A is fully programmable, allowing the user to create complex test sequences and can provide detailed and consistent error reporting. It can also run the unit under test at full speed. Basically, once the target system has a stable clock source and power supply, the pod can be attached and troubleshooting can begin. Many pods for common CPUs were produced, including C80, 6502, 6809, 68000 and so on. Each pod is a complete microcomputer in itself based on the same CPU the target machine utilizes. This allows the 9010A to natively interact with the UUT. The 9010A can perform all kinds of tests like electrical integrity of microprocessor bus, RAM, ROM, I/O. It can also try to map the memory space automatically using its learn function. More troubleshooting functions include read, write, toggling of individual lines, and more. Today, 9010As are becoming increasingly rare to find, and prices for the mainframe as well for the pods are very high. However, reproduction PCBs for the most popular pods like the C80, 6502, 6809 or 68000 are available. To demonstrate, we use a replica 6809 pod on a Ghosts and Goblins bootleg PCB set. To hook up the Fluke, you'll have to do the following steps. First, connect the pod to the mainframe, then power up the mainframe. This will enable the pod's protection circuits. Perform a pod self-test to ensure the pod is working correctly, and then remove the target system's CPU and insert the pod into the socket. The 9010A comes from a time when ICs and especially CPUs were a major cost factor. Also, machines used to be designed to be repairable. For these reasons, ICs, especially more complex ones like CPUs, were very often socketed, and therefore the installation of a pod would be simple and relatively non-invasive. Now power up the UUT. That's it. Now you can start testing. First, let's do a bus test. Looks like address bit 8 is tied low, so let's loop on the error. As soon as the fault is cleared, the 9010A will let you know by beeping and displaying a message. Do the bus test again, and it's good now. Now we can test the RAM. Here we test the main CPU's working RAM. RAM tests can be either short or long, meaning much more detailed. After about 2 minutes, the 9010A reports no errors found. ROM regions are tested using signatures. As mentioned before, there's also a learn function which can try to automatically map parts of or the whole address space and distinguish between RAM, ROM or I/O areas. ROM looks good too. So it appears nothing should keep the system from booting. Let's try to run it. As you'll see, the system will run at full speed using the pod's CPU directly. The probe allows further investigation of the UUT. It can serve as a simple logic probe by displaying logic levels, but can also calculate signatures from the captured data stream, which we'll show later on. As mentioned before, 9010As are becoming increasingly rare to find. While there are replica PCBs even for the mainframe itself, building the base unit leaves you with the problem to find a solution for the keyboard, display and power supply, which will increase the cost and complexity of any reproduction project significantly. This is why we chose a hybrid hardware-software approach to emulate the mainframe hardware using readily available parts. The basic idea was to build a fully functional, cost-effective emulation for the 9010A mainframe. It should offer all the functions of an original mainframe, but add modern-day features like networking and remote access. The FlukeEMU is a software emulation running on a Raspberry Pi. It uses add-on boards to interface with original or reproduction pods and the probe. The whole project is open source and freely available on GitHub. The main component you'll need is a Raspberry Pi. It runs the software emulation of the 9010A. Pi 3 is more than enough. The other thing you'll need is the FluCom add-on board or hat, which is used to physically interface with the pods and to provide power to the Raspberry Pi as well as to the pods. The system can be used standalone, even headless, controlled via VNC, or like in our case, mounted onto a little touchscreen display. The optional probe board adds the probe analog circuitry and utilizes a Raspberry Pi Pico microcontroller to emulate the digital parts of the probe logic. Speaking of the probe, there are also several reproduction projects such as our own. In this part of the video we demonstrate the emulator in practical use. First we'll again utilize the Ghosts and Goblins bootleg board and the Repro 6809 pod and perform the same series of tests we did with the original hardware, including bus, RAM, ROM test, and finally we'll run the UUT. To show how to run a test program, we'll load a very simple program into the 9010A and step through it. This just in and decreases the value for background scroll and was originally used to isolate a visual glitch only apparent while scrolling. To show a more complex program, we'll use an MSX board and a Repro C80 pod. To load the program, we'll first have to mount a tape file into the drive. Then we can load the program into the 9010A's memory. Running the program, it gives us different options. Let's choose the video display test. An Atari Asteroids board and the Repro 6502 pod are used to show more of the probe's functionality. First, we calculate a node signature. The probe has to be synced to either the read or write parts of the CPU cycle to do so. Then we clear the probe data. Next, the UUT has to be stimulated in a reproducible way. For this example, we simply perform a bus test. As you can see, this provides a consistent signature of CDCB. Another way to characterize a node is by using the probe's event counter. To demonstrate this, we use another test program. The probe board X is a still experimental variant of the probe board. It will allow the use of a regular BNC oscilloscope probe. You can set the sensing and pulsing functions to either of the probes, in theory even using the BNC probe to pulse and the normal Fluke probe to sense the pulses. Since oscilloscope probes obviously do not have LED indicators, display of the detected levels is provided on the emulator's main screen. You can also choose to have an acoustic feedback. If you don't like the touchscreen or miss the clickiness of using an original 9010A, just use a physical keyboard. All the keys are mapped, and if you forgot the mappings, just have the emulator display an overlay. Using a physical keyboard can make entering data much easier, especially when writing programs.